Hello, my dear students, and a very warm welcome back. It's your tutor Braya, and I know your exams are just around the corner, so today we're going to do a super quick, super clear revision of one of the most important chapters you'll face, laws of motion. Chalo, let's get right into it.
All right, think about this for a second. We've all been there, right? You're just standing in a bus, maybe holding onto a pole, and suddenly the driver hits the accelerator, and bam, you're thrown backward. Or he slams on the brakes, and you lurch forward. What's happening there? Well, it's not magic, it's pure physics, and today we're going to figure out exactly why that happens.
Okay, so first up, we have Newton's first law of motion. Now, to make this super easy for you to remember, I want you to think of it as the lazy rule. Yeah, you heard me right. Why? Well, because this law is pretty much all about how things just love to be lazy.
So this, laziness, it actually has a proper scientific name. The fancy word for it is inertia. You see, it's a basic property of literally every single object. It just means that an object will fight to keep doing whatever it's already doing. So if it's just sitting there chilling, it wants to keep chilling. If it's moving, it wants to keep moving. It just resists any change.
And this laziness, inertia, it comes in two flavors. Look here. On the left, you've got inertia of rest. It's just like this person sleeping so soundly. An object at rest wants to stay at rest. Then, on the right, you have inertia of motion. An object that's already moving wants to keep on moving at that same speed in the same direction. And that's exactly what happened on the bus, right? Your body wanted to stay put, inertia of rest. But the bus started moving, and that's why you felt like you were thrown backward.
So, here's the bottom line. The most important thing to get. Unless some outside force comes along and messes with it, an object is just going to continue doing its thing. If it's at rest, it's going to stay at rest. If it's in motion, it's going to keep going in a straight line at a constant speed. That's it. Simple, right? That's our lazy rule.
All right, let's move on to the second law. And listen up, because this one is the big one. I call it the hero formula. Why? Because trust me, most of the numerical problems in your exam, they're going to come from this law. This is the absolute superstar of this chapter. But before we get to the hero formula itself, we have to meet another key player, momentum, okay? The formula is super simple. It's just mass multiplied by velocity. Now, to really get it, just imagine this. Someone throws a cricket ball and a tennis ball at you with the exact same speed. Which one is going to be harder to stop? The cricket ball, of course. Why? Because it has more mass, which means it has more momentum. You can think of momentum as the josh, the real power that a moving object packs.
And that idea of momentum brings us right to our hero formula. So technically, Newton's second law says that force is directly proportional to the rate of change of momentum. But for your exams, the golden formula, the one you absolutely have to remember, is the simple version. Force equals mass times acceleration. F equals ma. I'm telling you, write this down, put it on your wall, memorize it. This is your key to solving a ton of problems.
Okay, so let's see this hero formula in the real world. You've all watched cricket, right? Think about how a great fielder, like Virat Kohli, catches a really fast ball. Do they just stick their hands out all stiff? No way. They always pull their hands back as they make the catch. So the question is, why do they do that?
Well, it's all about physics. By pulling his hands back, what is the cricketer really doing? He's increasing the amount of time it takes to stop the ball, to bring its momentum down to zero. And here's the magic from the second law. If the change in momentum happens over a longer time, the force felt by his hands is much, much smaller. So more time equals less force, and less force means, well, less ouch. It's a concept called impulse, and it's a perfect real-world application. All right, now, pencils out, eyes on the screen. Exam question alert. This is exactly the kind of problem you can expect to see on your paper. So let's walk through one together step by step. Okay, so here's the problem. We've got a bullet. We know its mass, its speed, and the distance it takes to stop inside a wooden block. Our job is to find the force the block puts on the bullet. So, how do we do it? Let's look at the steps. Step 1, we got to find the acceleration a. For this, we'll pull out one of our good old equations of motion. v squared minus u squared equals 2as. We plug in all the values we know, and we get our acceleration, which is minus 6,750 meters per second squared. Now don't worry about the minus sign. That just means the bullet is slowing down, it's decelerating. Now for step 2, we use our hero formula, F equals ma. We just multiply the mass, 0.04 kilograms, by the magnitude of the acceleration, 6,750. And what do we get? Boom, the answer is 270 newtons. See? When you break it down, it's totally manageable.
All right, 2 down, 1 to go. Let's get to the final law, Newton's third law. And for this one, the nickname is the buddy rule. Why? Because forces are like best friends. They never, ever show up alone. They always come in pairs.
And here it is, probably the most famous sentence in all of physics. I bet you've heard this 100 times, in movies, on TV shows, everywhere. To every action, there is always an equal and opposite reaction. It sounds so simple, right? But it's so powerful.
So what does that actually mean? Well, think about something as simple as a high five. When your hand hits your friend's hand, your hand is putting a force on their hand. Let's call that the action. But at that exact same moment, your friend's hand is also putting a force back on your hand. And that's the reaction. The key is, both forces are exactly equal in strength, just in opposite directions. You both feel the sting, right? That's a perfect example of the buddy rule at work.
Okay, now listen very carefully, Beta. This is a super important point. This is where so many students get confused. The action force and the reaction force act on different objects, right? In our high five example, the action was on your friend's hand and the reaction was on your hand. Since they are on two different bodies, they can never cancel each other out. Okay, please remember this. It's a common trap.
Awesome. So now we've covered all 3 of Newton's laws. Let's quickly look at how these laws help us understand a couple of common forces that you'll definitely see in your problems, specifically friction and the forces in circular motion.
So you all know friction, right? It's that force that always tries to oppose motion. But there are 2 main kinds you need to know. First, you have static friction. Think of it as a really stubborn force. It's what stops an object from moving in the first place. You push a little, it pushes back a little. You push harder, it pushes back harder, but only up to a point. Once you push hard enough to overcome it, the object starts to move. And that's when the second type, kinetic friction, takes over. And here's a cool tip. Kinetic friction is usually a bit less than the maximum static friction. That's why it's always harder to get a heavy box moving than it is to keep it moving.
Okay, let's talk about circular motion. Whenever something moves in a circle, say a car taking a turn, you know there has to be a force that's constantly pulling it toward the center of the circle. We call this the centripetal force. But here's a question for you. Is this some brand new, mysterious kind of force that just appears out of nowhere?
What do you think? The answer is a big fat no. It's not a new force at all. Think of centripetal force as a job description, not a name. It's a role that one of our existing forces has to play. For example, when a car turns on a flat road, it's the friction between the tires and the road that is the centripetal force. When the Earth goes around the sun, it's the force of gravity that's doing the job of being the centripetal force. See? And check out this diagram of a car on a banked road, like you see on racetracks. This is a perfect example of teamwork. Here, it's not just one force. If you look at the diagram, you'll see that a part of the normal force and a part of the friction force are both pointing towards the center of the turn. They team up, and together they provide that big centripetal force needed for the car to take the turn safely, especially at really high speeds.
All right, so let's lock it all in with a super quick summary for your exam. Ready? Newton's first law, that's our lazy rule. Objects want to keep doing what they're doing. Newton's second law, that's the hero formula, F equals ma. And Newton's third law, that's the buddy rule, action and reaction. If you just remember these simple nicknames, I promise you, the concepts will stick with you.
My dear students, you've done a great job today. You've gone through the whole chapter, you understand these concepts, you are going to do wonderfully in your exams. Just believe in yourselves. You've got this. Bilkul tension nahi lene ka, okay?
And just before we finish, I have one last little task for you. We talked about buses and cricket, but I want you to look around you today. Can you spot 3 other places where you see Newton's laws in action in your everyday life? Think about it. Let that curiosity drive you. All the very best, and I'll see you in the next one.